Can you see the screen?
Yes, sir.
Okay. Okay. So let's start our class. So in the last 2 or 3 classes, I was basically discussing about the origin of magnetic field and the nature of Lorentz force, particularly the kind of example that I have discussed in the last class, where we have considered a current carrying wire which lies along the x-axis in a laboratory frame, and the wire is electrically neutral. And we have seen that when we switch to another frame which is moving with respect to the laboratory frame, we find that the wire becomes charged, and we considered a test charge somewhere around that current carrying wire, which will not experience any force due to electric field or magnetic field in the laboratory frame. First of all, because there is charge and because the wire is neutral, so there will be no electric field surrounding the wire. And secondly, the test charge is not moving, that's why even the current carrying wire has a magnetic field associated with it, but the test charge will not experience any force due to it. But when we jump to another inertial frame, suddenly the current carrying wire, which was neutral in the laboratory frame, will become charged in the moving frame. Consequently, the test charge will experience a force due to electric field. So in the prime frame, the test charge should experience a force along a certain direction depending on the flow of current in the current carrying wire. So in order to maintain the relativity, I mean, you have two assumptions of relativity, which I mean, everything that we have derived in this course are just consequences of those things. And relativity, I mean, puts a constraint that this force must be balanced by some or counterbalanced by some other force in order to keep the force zero on the test charge. So we must have something like a magnetic field, right? So some force which we call magnetic field. Fine. From the moving frame, we see there is a force, and that force acts on the charge. Although the test charge is at rest in the laboratory frame, but it is moving in the prime frame, because depending on your motion of the prime frame, the test charge will move along a certain direction, and depending on the direction of motion of the test charge, it will experience a force which will balance the force due to the electric field, and the direction has to be such that it should cancel the electric field. And that's why this cross product, we have seen that the Lorentz force always acts along the perpendicular direction to the velocity as well as the magnetic field. So this is the reason behind the particular expression we have in the Lorentz force expression. So today I will discuss a couple of problems. Okay, so unless you solve some problems, the idea may not be clear. So let us start with a very simple problem. First, I will explain the problem, then I will solve it. So let us consider a line charge. Okay, some line charge. It's not a current. Okay, imagine a wire or which is basically charged in the laboratory frame. So a line charge with charge density say lambda per unit length. So charge density is lambda, is distributed along the x-axis in the laboratory frame, say S. So the wire or this charge, this line charge is at rest in the laboratory frame. Now, if I ask you to calculate the electric field and magnetic field due to it, it's a trivial exercise because you have done such problem in BSc. So what is the electric field near, say, infinite charged wire, right, of charge density lambda? You have done such problems. It's a straightforward problem. You just have to apply Gauss's law, right? So, and what is the magnetic field? Because the charged particles are at rest. Now, this is a line charge, and so you do not have any motion of charges inside the wire. So, do not have any current as such. So, magnetic field will be zero definitely in the laboratory frame. And what will be the electric field? So, let me draw the picture first. Let us draw the axis in the laboratory frame. So, suppose these are the axis, say x, this is y, and this is z. Let us call this frame S, which is the laboratory frame at rest. Now suppose that this charge, this charge, line charge, sorry, this line charge is lying along the x-axis, right? So it's some charge, okay, so line charge. The charge density is given to you. Say charge density is lambda, and if you know that, I am asking you to calculate, say, electric field and magnetic field somewhere at a point P, say, at a distance r. You can calculate it. So of course, the magnetic field, there is no doubt about that the magnetic field will be zero, right? So I can straight away write Bx will be zero. I mean B will be zero. So Bx, By, Bz, all three components will be zero in the laboratory frame. What will be the electric field? The x component of the electric field? Can anyone tell? What is the x component of electric field due to this line charge lying along the x-axis?
Integration lambda dx. 1 by 4 pi epsilon naught.
You don't have to do any integration. I mean, of course, you can do it in, I mean, several different ways. I mean, because you learn to apply Coulomb's law, Gauss's law, or say Poisson's equation. I mean, it can be solved in many different ways. But what I'm asking you, a simple question: what is the electric field? Okay, first of all, you don't have to write down Ex. Tell me what is E, electric field. What is the electric field at a distance r, say, from the wire? Electric field. How do you solve this problem?
Lambda by 2 pi epsilon 0 r.
Right. So that's a straightforward problem. Just imagine a coaxial cylinder, and then you take unit length. So basically, it is the Gauss's law, simple, straightforward, right? Of course, you can apply Coulomb's law, but since there is a symmetry, you should apply Gauss's law. That's what you have learned in your BSc, right? So electric field, the flux of electric field across the curved surface, I mean the cylindrical surface, will be E into 2 pi r, will be lambda by epsilon naught. R, I mean, E into 2 pi, I mean, R, definitely it has the area. So basically 2 pi R is the perimeter, and the length of the unit length. Just take unit length. So lambda, so basically let me write down it here. Lambda into twice pi R into unit length will be basically lambda by, sorry, E, electric field times the flux area in lambda by epsilon naught. So if this is R, this is one, so what he said is E equal to lambda by.
So lambda L by epsilon naught.
Lambda
Lambda L
L.
by.
This is not L. I have taken it's 1.
Oh,
Okay.
okay, sir. Yes.
So this lambda is a charge per unit length, charge density, right? If you put L, okay, you can put a L here, then you have to put a L here. L get cancelled, right?
Okay, sir. Yes.
Is it clear? Right. So lambda by epsilon 0 r. Fine. But what will be the x component? If I ask you, this is electric field. Fine. What will be the x component of electric field? What will be the y component of electric field? And what will be the z component of electric field? Let us write down it here. Okay. What is Ex? What is Ey? And what is Ez? Okay, you have to go to the picture in order to understand that. If I ask you, suppose this is some point, arbitrary point P, right? So how do you get the x component, y component, and z component? What is r here? If I ask you, so r is what? You have to remember what is the meaning of r. R is the radial distance, right? From here to here. Sorry. So this is the radial distance. What happened? So what is the radial distance? R. What is the radial distance? Suppose this point P has some coordinates, say x, y, z. I give that. So what is the radial distance? Radial distance from the wire.
Sir, we should root over x square plus y square plus z square.
Root over of, okay. So root over of x square plus y square plus z square. That will be the distance between the origin to this, right? Do you want to calculate that? Square root of x square plus y square plus z square would be the distance between the origin and this point. Do you agree with me?
Yes, sir.
তাহলে এটা কি হবে? I'm asking a very simple question. What is the distance between this x-axis to this point P? It's just simple geometry.
Z square y square square root.
Y square plus Z square.
Correct. Square root of y square plus z square. X, you see this point and this point has the same x coordinate, right? So when you calculate distance between 2 points, what do you use? x2 minus x1 square plus y2 minus y1 square plus z2 minus z1 square. Then take a square root of that. So both of these points have the same x, right? So x2 minus x1 is 0, right? And then you have I have already told you the coordinate is y here, and there is no y coordinate here, no z coordinate here. Y equal to 0, z equal to 0. So this will be square root of y square plus z square. Correct. This is the distance r. Fine. But what will be the x component? Sorry, yeah, x component, y component, z component electric field. See, what I'm asking is this is a very basic problem from your BSc. No, it's not a complicated problem, right? It's a simple conceptual problem from your BSc, where you have used Gauss's law to solve different kind of problems. So what is x component of electric field?
স্যার বলছি প্রথমে ওই ইলেকট্রিক ফিল্ডের ক্ষেত্রে এটা ওই ল্যামডা মানে ভেক্টর আর বাই আর কিউ করতে মানে ওটা স্যার আর স্কয়ার করতে হবে প্রথমে।
আচ্ছা আচ্ছা করে দিলাম, ঠিক আছে। What he is saying that I should write this like this. Okay, fine. কি করব? এটাকে আর স্কয়ার করতে হতো।
হ্যাঁ 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 স্যার
আর স্কয়ার, তাই তো? আর এটাকে আর করতে, তাই তো? ওকে, ফাইন।
হ্যাঁ স্যার।
I agree with you, fine. Good. So then tell me what is ex?
এবার স্যার আর ইকুয়াল টু স্যার স্যার আর ইকুয়াল টু আর ভেক্টর ইকুয়াল টু এক্স প্লাস এক্স আই প্লাস ওয়াই আই প্লাস জি।
Right.
কি করতে হবে?
You are in the right direction, but you have to. I mean, you say. You tell me. I mean, what are the? Yeah, you are right. You are right. So what are the x component, y component, z component? Is there any x component? You already have told me what is r, right?
স্যার এক্স কম্পোনেন্ট নেই স্যার,
Right. So this
স্যার
is
শূন্য হবে।
good.
ওয়াই আর
হ্যাঁ,
জেড
ঠিক।
কম্পোনেন্ট হবে শুধু।
হ্যাঁ, ঠিক আছে, কারেক্ট। এইদিকে তোমরা এটা জানো তো, এই যেদিকে তারটা পড়ে আছে সেদিকে কোনো ইলেকট্রিক ফিল্ড, এই ডাইরেকশনে ইলেকট্রিক ফিল্ড থাকবে না, রাইট? রাইট, পারপেন্ডিকুলার টু দ্যাট। হোয়াট ইজ ইউআই? ইউআই ঠিকই বলেছো। তাহলে ইউআইটা কি? সিম্পলি ল্যামডা, ঠিকই বলেছো, ল্যামডা ওয়াই ডিভাইডেড বাই টোয়াইস পাই এপসাইলন জিরো, হাতে লেখা খারাপ হয়ে গেছে, টোয়াইস এপসাইলন জিরো, টোয়াইস পাই এপসাইলন জিরো ওয়াই স্কোয়ার প্লাস জেড স্কোয়ার, তাই তো? কেন লিখলাম এটা আমি? আর স্কোয়ার আছে বলে, ঠিক আছে, ফাইন। y square plus z square, but r touches square root of y square plus z square, and ez will be similarly lambda times z divided by twice pi epsilon 0 y square plus z square. তাহলে আমরা তিনটে কম্পোনেন্ট পেয়ে গেছি। ইলেকট্রিক ফিল্ডের তিনটে কম্পোনেন্ট রেডি আছে, ম্যাগনেটিক ফিল্ডের তিনটে কম্পোনেন্ট রেডি আছে। Now if I ask you to calculate the electric field and magnetic field due to this charged wire in some other inertial frame. See, I can generate several versions of the same problem, but if you learn to solve one of them, you will I mean, you have the key, you can solve any of them. So let me start with a very simple version which we have solved similar problem earlier. So let us imagine a frame. Okay, this is the simplest one, where the frame is moving, this prime frame is moving along the x-axis with velocity v. Okay, so this is the simplest one, because you know the formula. I mean, everything is ready to use. So if someone in this frame measures the electric field and magnetic field at point P, what will be the measured values? You see, again, I should remind you, there is a difference between the problem that I discussed in the last class and this class, because in the last class I talked about a current carrying wire, right, which was electrically neutral. So there was no electric field inside in the laboratory frame. But here you see we have electric field in the laboratory frame and no magnetic field, right? Now from this frame, prime frame, if someone measures the electric field and magnetic field produced by this wire, what will be the values? You see, you may I mean wonder why should there be any magnetic field? Again, and that's trivial, because once you jump to this frame, these charges which are at rest in the laboratory frame will no longer be at rest. They will start moving, and once the charges starts moving, there will be a magnetic field as a consequence of relativity. So there will be both electric field and magnetic field in the prime frame. And if you want to calculate the values, it is straightforward because we already know the transformation. So what will be the electric field in the prime frame? Ex prime is Ex in this case, which are 0. So in that frame also Ex prime will be 0, electric field will be 0. What will be the y component of the electric field? It will be Ey equal to gamma Ey minus Bz. You see Bz is I think 0, right? Bz is 0. All B are 0. So I can simply write gamma into Ey. What is Ey? Gamma lambda y divided by twice pi epsilon 0 y square plus z square. This is the y component. And similarly, z component will be gamma Ez, right? Ez, and then I think it will be plus b and then by. Again, the second term is 0 because there is no bx, by, bz. So this will be gamma lambda z, very easy. So 2 pi epsilon 0 y square plus z square. Now you see this is these are the electric field and magnetic field. Okay, I mean very similar because the magnetic field, the parallel component doesn't change. Bx prime will be bx will be 0. What will be by prime? Again, I may not. Okay, I mean all these formulas are known to you, so maybe I will write one and then you can. By prime will be gamma times by plus vy c square times Ez. In this case, the first term will be 0, by is 0. So this will be gamma, Ez is lambda z, so gamma and then v lambda z divided by twice pi epsilon 0 y square plus z square, right? This will be the y component of magnetic field in the prime frame. But remember, in the prime frame, we usually want to write down the things in terms of the prime coordinate. So what will be the relationship between the prime coordinate and the unprimed coordinate? You see, there are no x prime here, only x here, y and z. And since y and z, they are orthogonal to the direction of motion, so y prime will be equal to y and z prime will be equal to z. So it is easier to write down the prime quantity in terms of the prime coordinates. Let us write down that. So y equal to y prime, z equal to z prime. That's why I'm writing z equal to z prime and y equal to y prime. So basically from this frame, when someone measures the coordinate, they will be x prime, y prime and z prime, right? Of course, the x prime will be different because of the relative motion, but y prime and z prime will be same. That's why we are able to write down y equal to y prime and z equal to z prime. And similarly, of course, I mean bz, I'm just writing the final expression, and bz prime will be similarly gamma times bz plus minus b by c square ey. Again, the first term will be 0, second term will be non-zero with a negative sign, minus. So these signs are important because if I give you a problem and if you produce a result with a wrong sign, that's wrong result. So okay, minus gamma lambda v and then y divided by twice pi epsilon 0 y square plus z square. And then have I missed something? Yeah, there is a c square, right? So I have to write a c square here, c square. And since y equal to y prime and z equal to z prime, I write y prime, z prime. So all three components of electric field and magnetic field are now known in the prime frame. You can see that the same problem can be put in different way. Suppose I give a problem where the prime observer is moving along the y-axis with some velocity v, or along the z-axis with some velocity v. Then only thing which will change are this transformation equation, right? You can straight away write those transformation equation from the equation itself, and then put the values to get a different set of electric field and magnetic field. Or say I can also change this problem in a different way, where I can put the charged this charge wire in the prime frame, right? I can put this charged wire in the prime frame, and then ask you to calculate the electric field and magnetic field in the unprimed frame. Of course, that is trivial because you just have to change V to minus B. So results will not, I mean, change dramatically. Only the change will be change of sign. But you should be careful about these things. I mean, once you understand the thing clearly, you should be able to solve any such problems, right? And also, I can give different combinations. Say, I suppose I have two wires, right? One with say charge density lambda 1, another with charge density lambda 2. So I ask you to calculate the resulting electric field, magnetic field for the laboratory frame observer and the prime frame observer. The same problem I can recast into many forms. But once you are able to solve one, and so you should practice these things. So there are no. If you go to different books, I cannot. I mean, give you a reference for a particular books where all these problems are there, because once I show you one example, you can have a different version of the same problem based on the same concept. So the problems which I am telling you are not from any book. I mean, you can I mean generate such problems easily by yourself. So so what I want to test is basically understanding. Right? How much you remember, that is not so important to me. Okay. If you put enough effort, you can remember anything. But the thing is that you have to understand. So that's my point. Fine. So this is one example I gave you, and I'm not discussing any other example. As you have seen what is the technique and what is the idea, you can solve those problems yourself. Fine. So one can also write this in a vector form if you like, because they have a very similar. So E will be, you can write E equal to, because this will be useful when we learn to transform electric field, magnetic field using that tensorial version of it, which I have not introduced yet, but I will discuss it soon. So you can write down, because the form is quite similar, y prime square plus z prime square, and then 0 y prime z prime. This is the electric field, and similarly magnetic field in the prime frame. I mean, I am just summarizing the results that we have calculated here, right? And this is gamma lambda times b divided by twice pi epsilon 0 c square, twice pi epsilon 0 c square, y prime square plus z prime square, and then 0 y prime z, sorry, minus, no, it's not y prime, this is z prime, right? That's wrong, minus y prime. You can see there's a minus sign there. This, for the z component, there's a minus sign with a y. So this is not 0 y prime z prime, this is 0 z prime minus y prime, right? So z component contains a minus y prime, y component contains a z prime. So fine. Let us now move forward. So actually, the thing which I am going to discuss now will be again discussed later, but I would like to take this opportunity to discuss this, because this is quite a simple thing to discuss about, because I have not discussed about the techniques how to calculate the electric field and magnetic field for a moving point charge. Because when we discuss about motion, it is quite general. The particle could be moving with uniform velocity, or the particle can have acceleration or deceleration. And how to calculate the electric field and magnetic field due to a moving point charge, that we have not covered yet. We shall discuss this I think within a month. So for the time being, I will discuss this simply because you see we are discussing about the inertial frame, where the frames are moving with uniform velocity. So now if I introduce a moving point charge, which is basically moving with respect to the laboratory frame with an uniform velocity, of course that is the definition of inertial frame, then can we calculate the electric field and magnetic field due to the moving charge? Because the kind of problem that we have discussed is basically transformation of electric field and magnetic field. So we are assuming there is some pre-existing electric field which is exerting force on some test charge, and then we are transforming them and calculating the forces. So that was the idea behind this application of transformation of four forces. But let us leave the concept of transformation of four forces for the time being, and let us discuss how point charge, when it moves with an uniform velocity, can produce electric field and magnetic field. Of course, it will have some electric field and magnetic field when it is at rest, but when it is moving, what will be those values? That we want to understand now. So so again, let me just explain this pictorially first, so that will make things easier to comprehend. So okay, I'm drawing some picture first. So we're going to calculate the field of a electric field and magnetic field, of course EM field of a uniformly moving point charge, moving point charge. See, we are not going to discuss the most general scenario here. Okay, so here we have a laboratory frame which is at rest, and we have a test charge. Okay, imagine a test charge. Okay, point charge, of course this is a point charge which is moving with velocity say v along the x-axis. And you see, we want to calculate the electric field and magnetic field due to this moving point charge, not the static one. Because if you consider a static charge, that is trivial, right? That then you just apply the Coulomb's law to get the electric field, and there is no magnetic field. But what we are interested in is to calculate the electric field and magnetic field due to a moving point charge, right? Now, this is not a very simple problem, but this particular example is quite simple because of this uniform velocity. Otherwise, things will become quite complicated. Okay. Okay. So let us attach an inertial frame with this moving charge. Okay. So I'm drawing a. So let us imagine that this point charge is sitting at the origin of the prime frame. So then I draw the picture in this way. So suppose this is x prime, and suppose that this is y prime, and suppose this is z prime. Okay. So we can simply use the transformation equation for the electromagnetic field to obtain the fields corresponding to the moving point charge in the laboratory frame. So first we have to write down the electric field and magnetic field in the prime frame. So let's call this S prime. Okay. Since the point charge is at rest, right? This point charge is at rest in which frame? In the prime frame, because that is the co-moving frame of the point charge. That is the rest frame of the point charge, which is attached to the point charge. So in this frame, the charge particle is not moving at all, right? It is moving in the laboratory frame, right? So in this frame, in the prime frame, if I want to write down the electric field and magnetic field due to this point charge at some point, say P, at a distance, say r prime, with coordinate x prime, y prime, z prime, then the point charge Q will produce an electric field at that point, right? And that electric field can be written as by using the simply Coulomb's law. So what is E prime in this prime frame? It is Q over 4 pi epsilon 0. Then, as you said, we can write it vectorially r prime by r prime cube, right? Because Coulomb's law is inverse square force 1 by r square. So I am writing r prime vector by r prime cube. And the magnetic field, of course, will be 0 because the charge particle is at rest in the prime frame, right? So the field is purely electric field. So you get a purely electric field in this frame. Now let us analyze this situation from the laboratory frame, that is the S frame, right? Now from the S frame, since the charge particle is moving, so it is obvious that we can have a magnetic field as well as a electric field. Okay, okay, maybe I can write down the components as well. If I, that will be simpler to write, because it will be easier to apply the transformation. Then I'm writing the components. So Ex prime, what is Ex prime? We just wrote down it a couple of minutes back, so this is quite similar. Ex prime is q, again x prime divided by 4 pi epsilon 0 r prime cube, e y prime is equal to q y prime r prime cube, and ez prime is equal to q z prime divided by 4 pi epsilon 0 r prime cube. And of course these will be 0. Bx prime, let's put a comma, bx prime will be 0, by prime will be 0, bz prime will be 0. Right, I'm writing this just simply because it will be easier to apply the transformation then. Right, you can apply them directly without writing them if you want. And now you see, you should also remember that, as I told you in the previous problem, because these two are different frames, s prime is moving with velocity v along the x-axis. So the coordinates of the point, if I take some point P, the coordinate of the point will not remain same in the two frames. So as the motion is only along the x-axis, so only the x component will be affected, and there will be no change in the y component in the two frames. So they will be same. So what will be the relationship between the x component and the y component? So when I write r prime, what is r prime actually? R prime is x prime square, right, x prime square plus y prime square plus z prime square root of that, right? That is r prime. R prime is the distance between this point charge and this point P, right? This is r prime. And if I want to write down the components separately, what is x, because we are using x prime, y prime, z prime, so I should write down what is x prime. X prime is equal to, if you apply Lorentz transformation, that will be x minus vt divided by square root of 1 minus v square by c square, or simply gamma is 1 by square root of 1 minus v square by c square, gamma times x minus v times t. This is x prime. Y prime won't change, z prime also will not change, z prime equal to z. Now if I want to calculate the electric field and magnetic field in the laboratory frame, then I have to apply the transformation of electric field and magnetic field, which we have derived in some previous class. So let us do that. You have to remember this, but I think it is easy to remember because all the magnetic field components are 0 here. Only the electric field components are non-zero, and they have a very similar form: x prime by r prime q, y prime by r prime q, z prime by r prime q. Okay, so it is easy to remember. So I'm going to next page. Okay, so in the laboratory frame, if I want to calculate the same quantities in the laboratory frame, in lab frame S, what is the electric field? Ex. See, we are going to apply the inverse transformation. The equation that we derived were the direct transformation. We are when I write a direct transformation, then the primed quantities are written in terms of unprimed quantities. And now I want to write down the unprimed quantities in terms of prime quantities. Since ex prime equal to ex, so of course ex will be x equal to x prime. Ex prime, and we know what is ex prime. What is that? I just wrote in the previous page, q x prime divided by 4 pi epsilon 0 and then r prime cube. But we know the value of x prime and r prime in terms of the unprimed quantities, because you want to write down everything in terms of the unprimed quantities in the laboratory frame. Because in the lab frame, I know what is the distance of the point P, what are the coordinate of it, that is x prime, x, y, and z, not x prime, y prime, and z prime, which are the coordinates from the prime frame. So if I do that, I have to write because q x prime is gamma into x minus vt divided by 4 pi epsilon 0, and then we have to write down this because r prime is square root of x prime square plus y prime square plus z prime square. And what is x prime? X prime is gamma into x minus vt. So this will be gamma square x minus vt whole square plus y square plus z square. Now remember, this is square root and we have a cube, it will be 3 half. And ey, of course, this will not be equal to ey prime. Ey will be something like this, ey prime, and there was a minus sign that will become a plus sign because this is an inverse transformation. So be careful about these things. These are very simple things, but people often do mistakes while writing these things. So ey equal to gamma ey prime, this will become plus because v will become minus v bz prime. And since there are no magnetic field in the prime frame where the charge particle is at rest, so this is 0. So I just have the first term over there. So this will be simply what will be that? Okay. Again, okay. So there is no gamma in the y term. We have only gamma. This gamma is coming from the s prime. So you will have q ey prime is q over, so gamma, I write q gamma y divided by 4 pi epsilon. This gamma is coming from here, right? This is not coming from y prime. And then we have gamma square, same in the denominator, x minus vt square plus y square plus z square whole to the power 3 half. And Ez is equal to gamma. Similarly, here it was a plus sign, so this will become a minus sign, Ez prime minus v by prime. See, in this case, you may not encounter any problem with the result, even if you don't write the correct sign, because you have the second term is a vanishing term, right? Okay, but whenever the second term is a non-zero term and the first term is 0, then there will be a problem, right? So but should be careful. So Vy again, Vy prime equal to 0. So I write q times gamma times z 4 pi epsilon 0, and then gamma square x minus vt square plus y square plus z square whole to the power 3 half. In a very similar manner, we can also calculate the magnetic field. So what is magnetic field in the unprimed frame? In the unprimed frame, the charge particle is moving, so there will be a non-zero magnetic field. Again, we can get those values from the transformation equation. X component remains same because the component of the electric field or magnetic field parallel to the motion of the charge doesn't change. So Bx will be equal to Bx prime, and Bx prime was 0, so of course Bx will be also 0. What will be By? By will be gamma times, again it's the inverse transformation, By prime, this was a plus, so this time it will become minus V by c square. You see, this time it will make a difference. And Ez prime, because in this case the first term is 0, second term is non-zero. So if I put a plus, that will be wrong result. So By will be minus gamma V by c square Ez prime. So this is, again you see, gamma times Ez prime is nothing but Ez. I have shown it earlier, right? Gamma times Ez prime is Ez. So this will be this, you can see this, right? Because this term is 0, so gamma Ez prime is nothing but Ez, right? So gamma Ez prime, I am writing Ez. because you want to write down the unprimed quantities in terms of the unprimed quantities. That will be easiest to write. So this will be again equal to minus of V by C square, and gamma Ez prime is Ez, and Bz will be similarly gamma Bz prime plus, this was minus, so this becomes plus V by C square. And I am reminding with this thing again and again, just because I have noted from my experience that these are very common mistakes, right? Equal to, this time it will be plus, so gamma V by C square Ey prime, and gamma, you see gamma Ey prime is Ey, so I write V by C square Ey. So I have written down the components of electric field and magnetic field in the laboratory frame, and these electric field and magnetic fields are the field components due to the moving point charge. These are not some pre-existing electric field. These electric field and magnetic fields are produced by the moving point charge. In the laboratory frame, the point charge is moving and it is producing some electromagnetic field, and these are the components. Let us see what are the differences. Okay, because okay, fine, we can see that okay, there is a non-zero magnetic field, that is easy to see, but what are the other important differences? Because when I see there is electric field, is it the same electric field that was observed in the prime frame? Because in the prime frame the point charge is at rest and producing an electrostatic field. Is that electrostatic field and this electric field are only differ by magnitude, or are there any other differences that you want to understand? To understand that, you see there is no, when I draw a picture, on the last page I draw a picture, right? So where this was the laboratory frame and this was the moving frame where the point charge was here, it is moving. So this distance is basically Vt at any particular instant. This was x prime, y prime, and z prime. Now you see there is no, I mean, special, I mean, once you choose the axis to be parallel with each other and the direction of motion, this is nothing. I mean, one can imagine this point was here before some time it was there, or before some time it was there. So it is moving, right? It is moving along the x-axis. So in order to understand the physical difference between the electric field produced in the two frames, it is easier to imagine a situation where, say, at particular time t equal to 0, at t equal to 0, imagine this point charge was or coincides with the origin of this frame. So it was moving, coming like this. So suppose I define my time as t equal to 0, this point charge is here. Say now it is t equal to 5 seconds, it is here, t equal to 10 seconds, it is here, and so on. So this doesn't change the physics in the, I mean, in the problem. It just giving you a simpler version of it to understand what is the physical meaning of it. Because otherwise, what will happen? You see this x minus vt factor. If you square that, it will be even a uglier term, and then you have to handle those terms, and you have to make them simpler to make a meaning out of it. So that's why I just want to drop this vt term. Why? Because that will not change the physics, because the electric field produced by the moving point charge remains same. Because I mean it's the same, I mean in the sense that the physics doesn't change. Of course, at this point, at that point, whenever if I take a fixed point, that distance between the point and the point charge will change. But what I'm saying, the nature of the electric field and magnetic field produced by the moving point charge will not change depending on where you consider the point charge to be. Right? The point charge is moving. So what I am assuming that suppose at t equal to 0, if I put t equal to 0, then this term will not be there. This moving point charge was I mean passing through the origin of the laboratory frame. Right? That is a simple assumption that I have made. Right? It will not change the physics. Fine. So if I do that, then I can actually write down a simpler version of this equation of electric field. I can combine them because simply you see this term will be I mean simply Vt term will be 0. So let us just combine them. So what will be the combination? You can see x, there is x here, gamma x, there is gamma y, there is gamma z. So you can take q gamma common, and you can, if you combine the x cap x plus y cap y plus z cap z, you get the r vector, right? Where r is the basically distance between the point charge to some point P where you want to calculate the electric field and magnetic field. Fine. So let us do that. Sorry. So I'm just combining the different component, right? So since the Vt term becomes 0 because of the assumption that we have made, so let us write down the electric field. So electric field, where in the laboratory frame, E will be Q times gamma times, as I told you, x cap x, y cap y plus z cap z, that will become R, and then divided by 4 pi epsilon 0, and then since Vt term is 0, this will be gamma square x square plus y square plus z square whole to the power 3 half, right? And we want to understand the physical meaning of this term in the denominator, because what changes does it make to the electrostatic field which was measured in the prime frame. Now, to get the physical meaning, you have to calculate this term. So gamma square x square plus y square plus z square, what is that, right? Okay, let me just draw a simple diagram to clarify the meaning of this. So suppose this is x-axis, y-axis, z-axis, right? Let us take any arbitrary point, say P, which at a distance r from the point. The point charge is here, right? At time t equal to 0, it coincides, both the s and s prime frame coincides at t equal to t0. The origin coincides. This is the distance. Suppose this is r, right? The frame is s prime, so both s and s prime are coincident at this time. So that's why there is, I'm not drawing two different frames, they are coinciding at t equal to 0. And this is r, this is point P, right? Suppose this r makes an angle theta, right, with the x-axis. This is x-axis, both x and x prime, right? This is both y and y prime. This is both z and z prime. This is r. Now, if I drop a perpendicular from this, you can decipher the components, because this will be x, this will be z, this will be y. Okay. So if I ask you what is x component, x will be simply r cos theta, right? X will be r cos theta. Now you see x square plus y square plus z square will be always r square, right? There is no doubt about that. It will be always r square. That means y square plus z square must have to be equal to r square sine square theta, right? Because you just write down this r square minus r square cos square theta, so r square into 1 minus cos square theta, that is r square sine square theta. And if we plug this here, what do we get? Gamma, again you can write this 1 over 1 minus b square by c square, 1 minus beta square, this is gamma square. And then we have x square, x is r cos theta, so I write r square cos square theta, and y square plus z square equal to r square sine square theta. So I write here r square sine square theta. Let us take this common. If I take 1 by 1 minus beta square common from the two terms, 1 by 1 minus beta square common, then I have to multiply 1 minus beta square with the second term. So that will give us, so r square cos square theta into the first term is 1 into this, that is r square sine square theta, and then minus beta square r square. See, you have to understand why I am writing this in terms of theta. That is important, right? It is not done arbitrarily, because I just find it easier to handle. That's why I'm putting theta. No, because you see, when we calculate the electric field due to static charge, then I mean, it's isotropic. You don't need to think about which direction you are looking at. I mean, the field is radial and it just goes as 1 by r square, so no problem at all. But in this case, there is preferred direction of motion. We will see that the electric field for the point charge will not remain same, and the direction of I mean the direction that this r vector makes with the direction of motion makes I mean important difference to the measured electric field. So okay, let me simplify this. So if we simplify this now, so what we get, so gamma square x square plus y square plus z square, this is equal to, let us write down that, equal to gamma square cos square theta plus sin square theta is 1, so r square minus beta square r square. Okay, I could have taken r square common, maybe next step, sin square theta. So this will be equal to gamma square r square and then 1 minus beta square sin square theta. Now let us put this in this expression of electric field and check how it looks like. So if I write down electric field in the laboratory frame due to the moving point charge, this will be q gamma r vector divided by 4 pi epsilon 0, and then we have simplified this because we have a power of 3 half over this expression of gamma x square plus y square plus z square. So you have to take a power of 3 half. This half, this 2 factor will get cancelled from both these two terms. That will give us gamma cube r cube. This is gamma. This okay, gamma cube r cube, and then 1 minus beta square sine square theta, beta square sine square theta to the power 3 half, right? Okay. Okay, I can separate it like I can also write this, because if I want to write down a unit in terms of a unit vector, I will write, okay, gamma square, and gamma is there, so one gamma will be cancelled, right? So this will be gamma square, right? I can straight away drop this. This is gamma square, gamma square. I just want to avoid another step. So gamma, this will become gamma square. So 1 by gamma square is again 1 minus beta square, right? So q times 1 minus beta square divided by 4 pi epsilon 0, and I am writing r cube to be r square into r. Why? Because I have a r vector here, so r vector by r will become unit vector, because I want to just compare it with this inverse square law, which we have in the static case, 1 minus beta square sine square theta whole to the power 3 by 2, and then r vector by r. So I have broken this r cube into r square into r, and this is the unit vector, just giving you the direction of the electric field, and it is radial, no doubt about that, right? So in the static case, you have electric field pointing from the point charge, so radially outwards towards all direction, right? This is inverse square law. So field amplitude drops as 1 by r square, and they are radial in nature, right? That is also preserved here. I mean, in the moving frame, the charge is at rest, and the electrostatic field is radial and inverse square and isotropic also. I mean, the electric field change in the same fashion along each and every direction as 1 by r square, right? They are proportional to 1 by r square, and they are isotropic. Isotropic means they change in the same fashion in all possible directions. But when you look at the electric field produced by the moving point charge from the laboratory frame, they will no longer remain same because of this theta dependence written here, right? So even the field is in inverse square, so 1 by r square is there, and radial in nature. So in this frame also it is radial in nature, but there is a direction dependence. It depends on the theta value of theta, which direction you are looking at, right? I can make an angle of 30 degree, I can get a different result. I can make an angle of 90 degree, I will get a different result. So the electric field no longer change in an isotropic manner in the laboratory frame. So that is one important difference that we have for the electric field for a moving point charge. Okay, let us simplify this a bit further to get some idea about the nature of the electric field that we have now. Let us take some extreme examples, extreme cases. For example, suppose theta equal to, say, case 1. Okay, so theta equal to 0. Okay, theta equal to 0. Okay, maybe I should write down the expression first, otherwise you may get again distracted. E was equal to q into 1 minus beta square divided by 4 pi epsilon 0 r square 1 minus beta square sine square theta whole to the power 3 half and r vector divided by r, which is unit vector, right? And for theta equal to 0, theta equal to 0 means, I mean, you see it's, you are basically calculating. So this is the frame, this is the point charge q, you are basically looking in the forward direction in front of the charge. So this is parallel, you may call it the parallel component, okay, of the electric field. So it's along the direction of motion, theta equal to 0, right? If I make a different angle, theta equal to 45 degree, this theta equal to 90 degree, this, and theta, depending on the value of theta, the electric field will change. It is 1 by r square, but this term is will be different, right? So theta equal to 0, if I put theta equal to 0, what do I get? So for theta equal to 0, you see this, the electric field along the parallel direction of motion will be simply q times 1 minus beta square. I'm not writing a vector sign anymore because it's a parallel. So I have already told you what the direction is. So that's why I'm not writing here this unit vector 1 minus beta square divided by, since sine 0 is 0, so simply this will be 4 pi epsilon 0, 4 pi epsilon 0 r square. So can you tell me what difference you are observing here? In what sense this is different than an electrostatic field of a static point charge? Is it larger than the static point charge? I mean, larger than the electric field produced by a static charge, or smaller than the electric field produced by a static charge, or is it same?
Smaller, sir.
Correct. So this is smaller. You can clearly see this 1 minus beta square term, and you may remember this thing we have also derived earlier, because this beta square term arises due to this relativistic thing, that is because of this magnetic field, right? I told you the second order term v by c square, right? That is the magnetic field that we can obtain also from the transformation of four forces, right? I have given you that example in some previous class. So smaller compared to the static field. This is smaller compared to the, that means the electric field becomes weaker in front of the point charge to the static field. It becomes weaker. And so here the lines of forces will be less dense, right? If I write down in terms of lines of forces, suppose this is the lines of force, right? They are less dense in front of the electric, in front of the point charge along the motion. And similarly, if I consider a second case where theta equal to 90 degree, that means we are looking at the orthogonal direction along the perpendicular to the direction of motion. Then you see the electric field will have a value theta equal to 90 degree. That means this is 1. So 1 minus beta square to the power 3 half. We can simplify this 3 half, and we have a 1 minus beta square on the top. So this will become square root of 1 minus beta square. That means this will become q over 4 pi epsilon 0 r square. You see this part is same. Only thing is the term in the denominator. This time we will have a term in the denominator, not in the numerator. That will be square root of 1 minus beta square, right? And you can see similarly that this is larger. This is not smaller. Larger than the static field. That means the lines of forces, I mean, you know that the density of lines of forces are directly proportional to the strength of the electric field. This lines of force concept was first given by Michael Faraday, and it is a very original and useful concept to visualize electric field. We still use these concepts, although I mean this is just a hypothetical concept in order to grasp the idea of electric field and magnetic field, but these are very useful, because you may be surprised to know that Michael Faraday, who used this concept just because he was not very proficient in mathematics. So he wanted to get an explanation for the kind of result he was getting. I mean, you know, the Faraday's law, right? How to interpret that? I mean, because he just wanted to visualize everything in terms of some physical picture, and that's why he invented this lines of force concept. Anyway, that's a different story which I do not want to go into. So what will happen in this case, what you will see that the electric field is larger, so that means the lines of forces will be get more denser here, they will be packed closer to each other, right? So in this direction they will be weaker, and in the orthogonal direction the lines of forces will be packed closer to each other. So that means the electric field becomes stronger along the orthogonal direction and becomes weaker along the parallel direction, right? And you can also check that if I put beta equal to 0, say case 3, where I put say, of course you can put theta equal to 45 degree, whatever, and then those will be just in between the maxima and minima of that. That's why I'm not putting those values, but you can check that. Case theta, case 3, where we check what will the corresponding value for beta equal to 0. When velocity is 0, of course the results will be same as the static case, q by say 4 pi epsilon 0 r square. There are no beta dependence, all the beta dependent terms vanishes because beta equal to 0, and this is where you have a e parallel equal to e perpendicular. So electric field along each and every direction changes in the same fashion. There is no direction dependence. So this is just same as the static field produced by a static point charge, right? Now, so we have some idea about the nature of electric field produced by a moving point, uniformly moving point charge. I should, of course, emphasize uniformly moving point charge. This is not an arbitrarily moving point charge, uniformly moving point charge, that you should remember. Now, you see, if I ask you a simple question, that suppose if I ask you uh, now suppose I ask you to verify some of the Maxwell's equation for this. Okay, so you know what are the equations satisfied by electric field and magnetic field. Those are the 4 equations, important equations that we have learned in the beginning of the course. So Maxwell's equations are known to us. So suppose I consider the Gauss's law. Gauss's law tells us that the flux of the electric field across a closed surface which encloses the point charge will be equal to 1 by epsilon naught times the charge enclosed by the surface. Now you see, when the charge is static, then the electric field is isotropic, right? Isotropic and inverse square. But when it is moving, it is inverse square but not isotropic, right? And we also know that okay, let me just draw a picture, then the things can be explained in a more clear manner. Let me just go to the next page, view page, new page after. Okay, view. Okay. So I'm just giving you a simple, although I already told you that the Gauss's law is not a correct law if you consider relativity. That I will discuss later, not at this stage, because we have to introduce the correction terms. So Gauss's law and Biot-Savart's law, I mean Coulomb's law, they're connected things anyway, because this doesn't incorporate the idea of causality in this. So I will discuss that in another class. For the time being, I'm just talking about the simple Gauss's law, which tells us that E dot NDS, that is a closed surface, take a closed surface around some charge q, what we get, E dot E is a vector, of course ds is an element of area, it has a direction normal to it, this is n cap, and ds, this is element of area ds, is equal to charge enclosed by epsilon naught. And so the charge enclosed, if I know the flux, I can tell you what is the charge, because they are directly proportional to each other just via some universal constant. So q will be simply epsilon 0 times the flux E dot n cap dA or ds, right? Now I also told you that the charge, this is from observation, that the charge is an invariant quantity. So if the charge is an invariant quantity, then whichever inertial frame you go, that should remain same, it's invariant. Now then it also says that whichever surface you choose, if you go to different inertial frame, you should get the same charge. That means you must have to have the same flux also, otherwise the charge will change. In order to have same charge, you must have to have the same flux, right? This is a constant. This is a constant, so I don't need to bother about this. So now, depending on the kind of surface we have to calculate the flux, right? And how then this is satisfied? I mean, how the charge will remain same, invariant? In order to have the same charge, you must have the same flux. Okay, let us take a very simple picture. Okay, let us imagine this is a laboratory frame S, and say this is the prime frame which we considered earlier, the moving frame S prime moving with velocity v, right? And suppose the charge point charge is here. Imagine a cylindrical field box, right? Some cylindrical field box around the charge. So this is our enclosed surface. Of course, you can take a sphere or some other. Here I am taking a cylinder just because the motion is along this. There is a nice symmetry. So that will be easier to understand. Of course, you can take a sphere or whatever surface you want to. So cylindrical field box around this charge. And if I calculate the flux in this frame, prime frame, you see in this frame the electric field is isotropic, right? So it is pointing towards all the directions in a nice uniform manner. I mean, they are inverse square and isotropic, right? But if someone observes the same point charge and the cylindrical field box from the laboratory frame, that person will find that the surface of the cylinder, so if I consider, I'm drawing the same picture here, you see since there is a preferred direction of motion where the prime frame is moving along the x-axis, so the x-axis will become shorter due to the length contraction. On the other hand, the y component or z direction will not change simply because they are orthogonal to the direction of motion. So the same physical system will look like this in the on prime frame or laboratory frame. So the difference is that these surfaces will not change because there is no change in the orthogonal direction. They are same. When you calculate flux, we calculate E dot area, right? Electric field dot the normal component of the area. So since the surface doesn't change, so that is not going to change here. But again, you see this curved surface, I should not call it curved because if you have learned differential geometry, the surface of a cylinder is not a curved surface, right? So I should not call it a curved surface. Let us call it a cylindrical surface. Okay, this surface. Okay, this surface will change definitely because the length has shrinked, right? So since the length is shrinked, so what will happen is that the total area of this enclosing surface has reduced. So then how do we have the charge invariance? That means the flux across the closed surface should remain same in both the frames. But here we can see that the surface area itself has shrunk. So how do we have the same flux? And that is taken care of by relativity. We don't have to bother about it because relativity, everything is coming from relativity. You see, the formula that I derived a few minutes back is telling you that the electric field is not uniform in the laboratory frame. It is anisotropic, right? In some direction it is stronger, in some direction it is weaker. So actually, if you want to calculate the actual theta dependence, you have to just take an integration of that, and that I am not going to do here. I'm just giving you a hand waving argument kind of thing so that you just get the idea. So what is that? Even if I don't write that theta dependence there explicitly, you know that the Ex prime doesn't change, right? I mean, Ex equal to Ex prime, that is known to you, right? Or Ex prime equal to X component. And the orthogonal components, I mean, this Ey is equal to gamma Ey prime, that we have also derived today, and Ez equal to, I am writing in terms of Ex, Ey, Ez, not E parallel or E perpendicular. Okay, I mean, things are identical if you write down the theta dependence explicitly, but right now I am not doing that. Gamma into Ez prime, right? So from this argument, you can see that the components of electric field parallel to the motion is not getting affected, but the orthogonal components are amplified by a factor of gamma, which is the Lorentz factor associated with the velocity of the particle. That means, I mean, the flux across this small cylindrical field box, I mean the top and bottom surface, are not going to change much. Of course, it will change slightly, because if you take that theta dependent quantity which I have discussed, where it becomes gets slightly weaker here and stronger there, then of course, I mean, you may see a small change. But again, if you take a sufficiently small cylindrical pill box, it is not going to change. Even if you take a big thing, then you have to use that expression which I have discussed in the previous page. For the time being, I'm just using the simple expression to explain you this phenomena here. So what is happening here? You see the area. How much? Can you tell me how much area will change? If I go from this frame to that frame, how much will be the change in area? What is the area of the cylinder? 2 pi r times L, right? But r doesn't change, because radius of the cylinder doesn't change, because it is orthogonal to the axis or the direction of motion, right? Only thing which will change is the length of the cylinder, L. So 2 pi r times L, and if I take L in this frame, the length will be shorter by what factor? By a factor of gamma, right? The length of the cylinder will become smaller by a factor of gamma in this laboratory frame, right? So the area gets reduced by a factor of gamma. But you see, the electric field in the laboratory frame are amplified by a factor of gamma here. So these two things compensate each other. Area decreases, but the electric field increases by exactly same factor gamma, right? So that's why they gets cancelled out, and the total flux across this surface remains same. Of course, if you take an arbitrary surface like this, it will be quite complicated to, I mean, prove this again, right? So then you have to take exactly this theta dependence and the exact form of the surface. You have to do it numerically. But this is just giving, I'm just trying to give you an overview of the concept that because of relativity, there is length contraction, no doubt about that. But again, this transformation of electric field and magnetic field, they are also a consequence of the relativity itself. So they take care of each other. So when the area becomes smaller, electric field becomes larger, so that the total flux remains same and the charge invariance is maintained, right? So the charge will be same in both the frames because the fluxes are same. Fine. Okay. Okay, maybe I should stop here and have a few questions, because I do not want to enter into a new topic today. Okay, so if you have some questions about what I have discussed in today's class, you can ask.
স্যার চার্জটা যে ইনভ্যারিয়েন্ট ওটা আমরা কিভাবে দেখাতে পারি মানে
No,
charge?
you cannot. No, you cannot prove it theoretically, right? Charge is the invariance of charge is an observational fact, right? And you see, in the relative, even here I see I'm not trying to prove the charge is invariant, right? What I'm trying to show you that the flux doesn't change, right? If the flux doesn't change, and if you take Gauss's law to be a fundamental law, then the formula itself tells you that the charge should be invariant. Although I should not say that this is a theoretical proof of charge invariance, right? What I'm trying to say here, since the flux is maintained to be constant across all the inertial frames, so from Gauss's law you can say that charge should be invariant quantity. But again, I mean, the invariance of charge largely comes from the observational facts. Okay, there could be many interesting questions, because you see, if I ask you, maybe I should or should not discuss this. Okay, you may think about this. Okay, it is not a part of this course. Okay, if I ask you, what about temperature? Okay, mass changes, right? If I ask you, mass is not an invariant quantity, right? Mass changes. What about temperature of a body? If I go from one inertial frame to other, what will the temperature will remain same or different? This is just some interesting thing. I mean, there are many interesting article on this. I think you can think about this from the perspective of, say, statistical mechanics. Okay, that would be an interesting exercise. Okay, anyway, any other question?
স্যার
বলো।
এখানে তাহলে কি চার্জ কন্টিনিউটি ইকুয়েশনটাও তো সেম থাকবে দুটো ফ্রেমে?
Continuity equation is talking about the conservation charge, right? Of course, you see, I mean, you see the things. What are the quantities involved in the continuity equation? That you have to think. Continuity equation ki bolo? Del rho del t, right?
ডেল ডট টি প্লাস ডেল
হ্যাঁ।
রো টি ইকুয়ালস টু 0।
রো ভি মানে কারেন্ট ডেন্সিটি আর চার্জ ডেন্সিটি তুমি কিভাবে, তার মানে একটা ভলিউম থেকে চার্জ যদি বেরিয়ে যায় বা ভেতরে আসে, তার একটা ফ্লাক্স রয়েছে, তাই তো? সেই ফ্লাক্সটা বেসিক্যালি চার্জ তো নতুন করে ক্রিয়েট হচ্ছে না, চার্জ বেরিয়ে যাচ্ছে বা ভেতরে আসছে, ডিপেন্ডিং অন দ্য চার্জ ডেন্সিটি ইজ ইনক্রিজিং অর ডিক্রিজিং, রাইট? ডাইভারজেন্স অফ, তোমার তুমি রো ভি নিচ্ছ, তোমাকে রোটা হচ্ছে গিয়ে তোমার চার্জ, ভিটা হচ্ছে ভেলোসিটি। সো তুমি যে কোনো ফ্রেমেই যাও না কেন, তুমি ইন্ডিভিজুয়ালি তুমি দেখো velocity is of course depends on the frame to frame, right? Because we have relativistic velocity addition formula. Density, I had told you how the charge density is a component of the four current density, time component rho c আমরা আগের দিন লিখলাম না যে চার্জ ডেন্সিটি, কারেন্ট ডেন্সিটি, আমরা পরে আসবো ওটাতে, যে j mu, what is j mu, right? Rho c and then jx, jy, jz. So these are the four components of current density, which is a four vector, right? So you don't need to think about charge density separately. Whenever you deal with charges, it is easier to think in terms of the four current density, because I mean this obeys this Lorentz transformation, and it will be easier to simplify the problem, right? So charge conservation, of course, it holds in each and every frame, no problem, doubt about that. Okay, if you have no other questions, we can continue in the next class. Do you have any other question? Hello. Okay.
No, sir.